Welcome to the Build Test Solutions webinar series. This episode focuses on the unique challenges presented when measuring the performance of heritage or historic buildings. Presented by Luke Smith, Managing Director of Build Test Solutions, and moderated by Tanya Jain, Head of Marketing, this webinar will highlight how measuring doesn't have to be a disruptive process, but will give surprising insight into the fabric of these unique buildings.
Hello, everyone. Yeah, my name's Luke Smith. I'm Managing Director here at Build Test Solutions. And in today's talk, we're going to delve into how we both define and then go on to kind of measure and understand the thermal performance of traditional and heritage buildings. So I'll try and keep the talk to about 30 minutes. I think the most interesting bit is the Q&A and the open discussion at the end. So three main sections that we'll cover. I think it's really important that we get into how we actually define a traditional heritage building, and then from that, kind of what's the associated kind of problem, challenge / opportunity with these types of buildings. And then, of course, once we've defined and understood that we are actually dealing with a traditional heritage building, how do we go about understanding them? What's the kind of status quo, business as usual approach, and how might we challenge that and go on further with measurements? And then we'll try and bring it all to life. The final section with looking at some case studies. So how do we define a traditional or heritage building exactly? It's actually, like I said, it's really important that we deeply consider this. I think traditionally or typically you would regard a traditional heritage building as one that is either old or listed in a conservation area. And that may well be the case in a lot of instances, but it's not always the sole reason why you might kind of categorize a building as traditional or heritage. So there's some great tools out there. So there's a British standard dedicated to exactly how you go about assessing the significance of a building, BS 7913. So if you haven't already seen that, that one's definitely worth a look. And then PAS 2035 Annex E goes on to present quite a nice kind of condensed version of that British standard as well. That is well worth a look. And we've got that definition on the right hand side there, pulled from Annex E of PAS 2035 2023. A building's significance is the value it has for today and future generations. This might be due to the dwelling's design and construction. It could also be craftsmanship or its association with a historical event or person or cultural practices. So like I say, it's not necessarily always just that a building is defined as traditional because it's listed or in a conservation area. It could be for other kind of historical or cultural reasons or particular kind of architectural significance. And similarly, in the majority of cases, these are going to tend to be older buildings, and by definition then constructed with natural materials, stone, brick, timber, and lime. But again, not necessarily always. You do of course have newer buildings constructed with more modern methods of construction that are equally significant and whether that's protected or otherwise. So then, we're always seeking to treat these buildings sensitively, upgrade them sympathetically, and ideally in a way that's reversible, that protects their character. And so, I think the main point here is that these aren't always necessarily grandiose Tudor manor houses or sort of places of huge significance like the Albert Docks in Liverpool, or sort of fair-dressed Edwardian Georgian terraces. We are also dealing with a whole raft of properties that visually you might not necessarily deem to be significant, but they are in a conservation area. They do represent sort of cultural significance or otherwise. So yeah, the whole selection of properties just kind of illustrated here may be regarded as traditional heritage buildings. And here's the excerpt from PAS 2035. So a framework for how you go about this assessing significance. Okay, so it's a really sizable subject area. It obviously requires a lot of specialisms. There are a whole host of organisations out there that publish some fantastic guidance and support materials and yeah, tools that can be used to support us in how we go about looking at and understanding and acting in relation to traditional buildings. Just taking kind of the older building example, I think there's approximately 6.5 million pre-1919 homes in this country, so 20% of the total built stock. So we're talking, yeah, a really significant chunk of homes for which, yeah, there are some bodies doing some great work, given the significant number of them. But yeah, today we can talk in particular detail about what we understand from having carried out lots of measurements of these buildings. So by definition, we know traditional buildings are unique, they're many and varied, and they require tailored solutions. So there are no two traditional buildings, heritage buildings that are the same. We're talking about, yeah, buildings that can be many years old that have been altered and treated in weird and wonderful ways that require tailored solutions, and tend to be sort of by their nature limited documentation, very little known about their construction details, given their sort of the potential sort of architectural significance, cultural significance. These aren't necessarily buildings that have been actively investigated, pulled apart, boroscoped, drilled, core sampled, that kind of thing. There's a lot of unknowns with these buildings, and so they're by proxy hard to model accurately. You can't necessarily readily apply default performance parameters from RDSAP and SIBSI lookup tables and performance libraries. And so we've got the challenge, therefore, of how do we better understand these buildings and balance that challenge of preservation and improving their energy performance. And of course, as many of you will already appreciate, kind of moisture risk management in these types of buildings is also mission critical in terms of particularly where the natural building materials are involved. The last thing we want to be doing is locking in damp problems or hindering kind of the vapor permeability of materials and yeah, creating sort of wet and dry rot problems and ventilation issues and so on. So yeah, moisture risk management, sorry, is really important in this field. So there we go. So over 30% of homes in the UK are older or traditional heritage buildings, more than 7 million properties in total. So a really significant opportunity area. Okay, so how do we go about understanding these buildings then? So I like to use the three M's. You've got modeling, measurement, and monitoring. So many of us will be familiar with conventional survey techniques, widely practiced, business as usual. We would go into a building as building surveyors or retrofit assessors, energy assessors, consultants, and we can carry out visual inspections to make professional observations, judgments as to what we observe, and record that in the form of a building survey. We might enhance that a little bit sort of with non-invasive kind of moisture surface spot checks and things like that. But yeah, generally, in sort of a visual inspection-based survey is by far the most commonly practiced assessment technique of the buildings. And then we would go on and typically create a model of that building with that sort of surveyed information. So whether that's generating something as simple as an RDSAP-based energy performance certificate, or through to a full-blown dynamic simulation model, or a BIM model, or a PHPP, passive house planning package model. Doesn't matter what tool it is that you're doing a model or a simulation in, you're tending to populate that with those observed building traits at the visual inspection survey level, or you're using lookup values from libraries. What I'm going to go on to talk about now in a bit more detail is that we can, of course, step that up a level and go on to measure in situ performance. And by measurements, we mean point in time testing of particular component parts of the building. So we could measure in situ U values, we can measure in situ air tightness, we can also measure the heat transfer coefficient of the building, or ventilation flow rates, and so on. A little bit extra work above and beyond doing a visual inspection, but giving you that much more sort of tailored, specific insight into the performance of that individual building. And then less practice still is the notion of monitoring. So this would be kind of longitudinal monitoring of indoor air quality, energy consumption, those kind of parameters over a period of time. So obviously there you're encapsulating the variations induced by weather and occupancy and sort of behavioral effects, and observing how internal conditions are kind of tracking over a period of time. Are we underheating in the winter, for instance, suffering from overheating in the summer? How does the building perform over the course of the seasons? This chart here on the right hand side shows a study we carried out with the Energy Saving Trust, looking at 587 buildings, comparing whole building heat loss rate, HTC, as measured versus what would otherwise be predicted by RDSAP. And you can see here there's a fairly clear linear relationship. So if there was perfect agreement between the modeling and the measurement, they would all be on that solid black line. You can see the dotted line is a true trend line through the points, and you can see that is trending slightly below. And so essentially models have a tendency, in broad brush terms, to overestimate heat loss in buildings. And then if I draw your attention just to the points more to the right-hand side of this chart, those with higher heat loss, which you might regard as being those older, poorer performing buildings perhaps, there's actually a much wider scatter. So you're getting actually some quite significant swings both above and below those lines. So this is again that kind of notion that EPCs and models, simulations of buildings, the default values that we know and love, they're okay on average as a guidance tool, but they fail to recognize the uniqueness of any individual building. So yeah, you pick any one of those points, and as much as the agreement's okay on average, you could be much higher heat loss than the model otherwise assumed, or conversely much lower heat loss, and that's going to drastically impact what package of interventions you might choose to go for. And I couldn't help but pull this quote in. So the STBA, Sustainable Traditional Buildings Alliance, produced a fantastic report all the way back in 2012 called Responsible Retrofit of Traditional Buildings. And so, yeah, over 13 years ago now, this was stated in that report. The performance gap between the model of a traditional building and as-built reality may be considerable, but it could also be the reverse of the performance gap that has been identified for new buildings that do not achieve anything like their predicted design targets. It would seem that in practice, traditional buildings often perform much better than predicted, owing to processes and interactions that are not well captured by models. Yeah, I think that's, again, research that was done some time ago, and yet that's kind of what we are proving out with more and more data today. Okay, so to truly understand the traditional building, we must prioritize measurement over assumptions. That is the crux of our message here. So tools exist today to allow us to provide data-driven, measurement-based assessment of buildings, and it needn't be the complex sort of academic-led building performance evaluation processes that we've maybe become accustomed to. There are tools and techniques that are accessible, affordable, can be used at scale on buildings to understand performance without the disruption and invasiveness of otherwise pulling these buildings apart in order to understand them. Okay, so that chart I showed you, the study we did with the Energy Saving Trust, that was a comparison of modelled versus predicted HTC, so the total rate of heat loss from a building. The product we used to do those measurements was Smart HTC, which is this technique for measuring the whole building heat loss rate. This is essentially a 21-day test. We need 3 weeks worth of internal ambient temperature data paired with total energy consumption during that period, and we can return both a whole building heat loss rate measurement as well as an assessment of the peak heat load of that building. Such a measurement isn't going to tell you specifically where the heat loss is going, but it's a really good barometer of the overall efficiency of the building, the overall fabric performance. Is this building hemorrhaging heat, or is it actually conserving energy relatively well, and the high energy consumption is more so to do with the services or energy use behaviours in that property? So we make this available to energy assessors, consultants, building surveyors, architects through a browser-based user interface. It's sort of low-cost pay-per-property model, and the method has been independently tested and validated, and it's otherwise referred to as a SMETA technique that Smart HTC was used under the DESNZ program and ranked very favourably as part of that project. Alongside Smart HTC, if you go into the trouble of doing this 3 weeks worth of internal temperature monitoring to spin up the thermal performance measurement, the loggers that we provide also capture relative humidity, and that's pretty common of sensors to combine temperature and humidity. So we can use that same 3 weeks into data to also return a mold risk score for a property and predict anticipated kind of surface condensation potential. And so in that, you've got a very discrete, low-cost way of just assessing the headline performance of a building. Beyond that, we could get into measuring and understanding the in-situ U values. So another product we've developed in recent times is Heat 3D as a way of measuring the U values or the heat loss rate specifically through walls or floors. It's currently in development for ceilings, but the main kind of priority has been to get it functioning and able to offer measurement of walls in particular. And so if let's say you've measured your HTC, you've understood that there's a high heat loss problem, you then might want to delve into understanding specific components of the building. So this Heat 3D method runs for 1 hour as a survey run off a tripod, pointing at a given wall of interest, a segment of wall of interest, and from that, just that 1 hour survey can return a measured in situ U value. And being thermography based, you're getting that much more sort of granularity. Sort of the U values are plotted at kind of a half-meter interval grid across the image, and you're able to then not only obtain that quantified kind of measured U value performance, you're seeing kind of how homogeneous that wall is and how uniform the performance is across the element. And are there any kind of notable defects? And I've pulled in some data here. These aren't actually studies that we've done, but again, it helps reinforce the point. So we've collated a few studies here carried out by the BRE and Historic Scotland, again, getting on for 10 years ago or so, all of pretty meaningful sample sizes. And so here, if we just take the top line, BRE conducted a study, 50 properties, looking at standard solid brick wall properties. They observed a mean measured U value of 1.74, and that's what has gone on to ultimately influence the default values we know and love in RDSAP. But actually, you can see here there's a standard deviation on that value, and actually the range that was measured was the lower bound U values were 1.38, upper bound 2.1. We've then also highlighted in yellow here a separate study commissioned by Historic Scotland, also looking at solid brick walls, a slightly larger sample of 85, higher standard deviation here, a lower bound of 0.94, upper bound of 2.2. So you're seeing here for something as simple as a solid red brick wall, U values anywhere between 0.94 out to 2.2, encapsulating those two studies. And then we've got non-standard solid wall studies carried out by same research teams, again observing really wide ranges in measured U values. So it's one thing to look at these mean values and take them as read, but actually, as you would expect, there's a uniqueness to every wall construction. Yeah, obviously, how wet is the wall, how the density of the bricks used, may there be a slither of air gap or trapped air between the leaves of the bricks, all influencing the ultimate sort of performance of that solid brick wall. And so you can see that here in this chart at the bottom, the distribution of U values across those solid brick walls. And then we've gone on to say, okay, what implications would those variations have on your EPC, for instance, if you were to plug that range into your model? So for a solid brick wall, if you inputted the U value of 0.94 or a U value of 2.2, you've got a difference here of 6 SAT points. You could be anywhere between 68 and 62 on your SAT point rating. In this case, both the particular building example used, both would remain in a PC band D, but a difference in the modelled running cost of £229. And so that you can see how that propagates through this table. Variations in U value, given that walls in particular represent quite a large surface area of the overall construction, is having quite a significant effect on the modelled outcomes, and that will of course go on to influence the simulations that you might run in terms of the appraisal of if you were to apply further insulation upgrades to those walls or not. And so yeah, quite stark impact on the end modelling just by changing that one measured U value, let alone also plugging in measured air tightness and so on. We've also got the pulse air leakage testing technology, so a compressed air-based system for measuring air leakage. The technical USP of this is that we're measuring directly at 4 pascals, so understanding the air leakage rate directly at conditions that are much closer to ambient pressure levels. Really quick, simple, easy to use test, non-invasive, so can be used in occupied homes, and approved for use both under new build and retrofit standards such as PAS 2035. And again, here from us having this technology, we've seen the sort of tests coming through. We're sat on a sample of about 170,000 air tightness tests now. On this chart on the left-hand side here, you can see the distribution of this is actually a slightly smaller subsample of those tests, but yeah, a good number of homes here. The mean air permeability is 8.3, but you can see quite a wide distribution on that. And just to emphasize that further, so here we've got just taking a particular construction of solid wall properties and then the built form of semi-detached, so either sort of end terrace, semi-detached built form. You can again see here that, okay, the mean measured air permeability is 8.9 for this very specific construction and form, but we could be encountering anything from an air permeability of 2 all the way out to 20 at 50 pascals. And so again, the mean is somewhat instructive, but really who's to say you're not in that property that's so much more airtight or vice versa. And again, that's going to influence what actions you might subsequently take. And airtightness is one of those things that you can't possibly walk into a building and make a judgment on. You can't observe airtightness. And yeah, just to really hammer home that point, here we've got two terrace properties, visually very similar, on the same street, exactly the same principal construction and built form. One is measuring an air permeability of 4.36 at 50 pascals, and yet this second one is measuring an air permeability of 10.9. So again, I think you're going to act quite differently with those measurement results in terms of what you would prioritize in going on to treat those homes. I wouldn't be surprised if, for instance, if both of those were reliant on intermittent extract fan ventilation. They clearly both had upgraded UPVC windows and doors and so on. That more airtight property at 4.4 is going to be really struggling for adequate ventilation. Whereas, rightly or wrongly, the more leaky home at least has that higher level of infiltration providing ventilation. But again, if you go on to tighten that property down, improve the air tightness, which is obviously a right thing to do from an energy efficiency perspective, again, you need to be mindful of the impact that's had on the air tightness and what the subsequent appropriate ventilation upgrades might need to be. And so then on that subject of ventilation, we have tools also for measuring ventilation flow rates. So we're a reseller of ASIN equipment. So this is a Netherlands-based company manufacturing bolometers or anemometers for measuring the flow rates delivered by mechanical ventilation fans. We supply these with a UCAS certificate as required by Part F of the building regulations. And they're both great bits of kit for measuring both the supply and extract rates delivered by those ventilation fans. Because again, you might think that, well, I know the make and model of a given fan, I can just look up its sort of specification on the internet or from the manufacturer, but does that fan do what it says on the tin? Is the motor performing as intended? Is there any resistance on the system that's limiting the flow? Have the fans been maintained sufficiently, and are they working as intended? Does it do what it says on the tin? So like I said before, management of moisture risk is critical in all buildings, but particularly traditional buildings. Sometimes lack of ventilation is just really obvious, and you can go about doing that, rectifying that quite readily. But again, more common is that you tend to fail to kind of appreciate the balance between airtightness, or you're underestimating airtightness. You think a building is more leaky than it actually is, and then you're misjudging the ventilation needs as a result. So those airtightness and ventilation measurements really go hand in glove in making sure that you're managing that moisture risk. You often hear people comment that older buildings in particular, they're designed to breathe. We shouldn't make them more airtight, and that can be detrimental to the performance. I think it's misleading to use the terminology breathe. It's actually appropriate that we do pursue good levels of airtightness in these buildings from a comfort perspective and an energy efficiency perspective. It is just about ensuring that you complement that delivered airtightness with appropriate ventilation, purpose provided controllable ventilation. And I think the breathability point also kind of stems from the fact that we also often recognize that you've got the separate challenge of vapor permeability in particularly kind of older traditional buildings. So again, these things aren't to be confused. It's absolutely improve air tightness, absolutely complement that with the right ventilation. But then you've also got the very, very separate matter of ensuring that any materials applied to the building fabric are not hindering the overall vapor permeability of the structure. We don't want to be trapping moisture in the building or prohibiting the kind of diffusion of moisture through the structure. So that's very separate subject of using vapor open materials, natural materials on these older buildings. Okay, so just moving on then and thinking about sort of, okay, what does this all mean in practice, and how do we relate to this on the ground? I've just got a few case study examples. Here we have Gresson Hall Museum in Norfolk. We supported Personnel Architects in carrying out an assessment of a series of buildings on this site. Walls typically present the largest overall heat loss surface area of most buildings. And obviously, as we've already touched on, U values can be really hard to determine, particularly structures like this where you've got bare stone kind of flint walls that, who's to know? Okay, you can measure the thickness of that wall build up, but when you've got plaster lining internally, what's in the middle of that makeup? Is it loose rubble? Is there a cavity or not? Is it solid? What is the inner leaf? Really tricky to know. And here we've measured a U value of 1.2, and that would be half what RDSAP assumed at the time under RDSAP 9.2 of 2.4. RDSAP 10 is doing better at recognizing the thickness of the walls now, so that would come down a little bit, but it wouldn't bring you down as close to the measured 1.2. And so I think immediately there you really have to question kind of the investment case for insulation. Clearly, this is a hard to treat building, but with that measured U value insight, I really don't think you would kind of contemplate kind of internal wall insulation to push that much harder, or perhaps you could get away with kind of a cork plaster or a thinner, more kind of sympathetic kind of internal lining, and not necessarily feel the need to push the thermal performance too hard. And so, yeah, those measured U values are helping inform the specification around insulation upgrades in that case. We've also had the pleasure of supporting the team at Westminster Abbey in measuring a number of buildings on their site. The most notable was the Deanery building. We also looked at 8 other sort of the little cloister residential buildings on that site as well. But the Deanery, we measured air tightness with pulse and ventilation, flow rates with Ventaflow. We observed a measured air permeability of 10.46. So the Deanery, it's a real mishmash of construction types. Actually, there's one of the wings is 13th century original kind of stone construction, and then you've had all these kind of I think the site suffered from quite severe bombing during the war, and so it's been patched up and reworked a number of times, and so it's had sort of a degree of rework and also fit out over the years, and it's extremely well cared for and well decorated internally. So it will have been replastered, and undoubtedly it has got new floor finishings, and window seals have been well looked after, and so so it's actually a reasonable level of air tightness despite it being hundreds of years old. And then to complement that, we're observing low mold risk. So the ventilation flow rates were okay, and the observed mold risk was low. And then really interestingly, we observed again really low measured U values. So that 13th century wing, the image in the top right there, those stone walls were measuring as U value of 0.9. So again, whilst you might have otherwise thought, do we need to do internal wall insulation linings in grand living spaces like the one in that bottom right hand image, potentially kind of conflicting with sort of architraves and cornices and skirting boards. I really don't think at 0.9 the investment case and the disruption is necessarily worth it. And then in other sections of the building, it was deemed to be solid brick walls, but there were timber internal linings, and again they was seemingly doing quite a good job of trapping air, because we were measuring U values there of 0.75. Again, potentially sort of underlining the investment case for insulation. So the consultants involved in this project went on to use those measurements to better calibrate their energy models. So you still need an energy model, these things go hand in glove, but you can improve the accuracy of them by inputting measured values, and then using that for more informed kind of option appraisal. We've had Field and Clegg Bradley Studios using Heat 3D to measure U values across a whole host of interesting projects, one of which was the Maritime Museum in Liverpool. Again, what they found here was that the walls were essentially wedge shaped, so really thick at the base, down into the dock, almost a metre thick in places, tapering to thinner walls towards the top. So they were measuring different U values on every floor, with a range of 0.66 through to 1.51, whereas RDSAP 10, the latest version, would have otherwise just flat assumed all U values to be 1.1 across that building. And again, that's informing the investment case, and led the architect to specify less insulation and prioritise sort of some of the sort of alternative expenditure elsewhere, other interventions. And then, so they're not all our case studies. It's a bit of a wordy slide, but the University of Salford and the National Trust published a paper earlier in the summer. As a team, they looked at 9 solid wall pre-1919 homes, and 3 of which were semi-detached, 6 detached properties, pretty sensible floor area range, 72 through to 245 meters squared. These weren't, it's not a collection of properties on a single site. These were just a random sample of nine homes. And again, the team there, here they were actually using blower door fan air tightness test methods and heat flux plate based U value measurement methods, and they were observing discrepancies of up to 47% on U values, 49% on air tightness, and that having an impact on the energy demand and running cost predictions of circa 24%. So U values were, the deviations from the RDSAP defaults were anything from 0.99 through to 1.67, 12 to 47% better than assumed. So again, we kind of, as much as we see it in our own data, we're seeing this trend elsewhere in other studies, and it's again what the STBA, Traditional Buildings report, alluded to, is actually the more and more we measure these buildings, it becomes clearer and clearer that default values are quite conservative, and existing buildings, particularly walls, tend to perform better than you might otherwise have assumed. Air tightness on this particular project was more variable, so 7 out of the 9 properties it did outperform the models. The models were more, the reality on the ground was that the buildings were more airtight than the models would have us believe. But there were, the remaining 3 properties, the remaining 2 properties, sorry, were actually worse than assumed. So again, it does go both ways. I'm absolutely not sat here today preaching that do measurements and it can get you out of jail in terms of upgrades. It's about just making sure that we're appreciating the nuance of these traditional buildings and tailoring solutions accordingly. So just to wrap up then, and we can move on to some Q&A. So in terms of how to access some of these tools that I've discussed, Smart HTC, Pulse, Heat 3D in terms of U value measurements, we do host directories on our website where you can find a sort of national network of testers with the equipment, with the training, who can support you with getting access to these homes and minimizing travel arrangements and doing the measurements on your behalf. Similarly, a good number of installers are increasingly picking up the capability to do measurements themselves, which is encouraging to see, for their own quality assurance purposes, and allowing them to offer their own kind of energy audit and assessment services. And yeah, that's I think as we increasingly shift towards a world of procurement being based on outcomes, and just last week we had the National Audit Office issues around alerting us to the issues around quality of retrofit. Installers being equipped with these technologies is only a good thing. Or of course, there's the opportunity to bring some of these tools in-house and upskill your own team to be able to do these measurements on your own traditional heritage buildings. BTF simply exists to bring about the measurement tools and help you specify and source the measurements, essentially. So to wrap up then, heritage buildings clearly are complex, unique, and require measurement before any intervention. I do appreciate measurement comes at an additional cost. You're spending more time upfront to understand the building, but the benefits longer term of that are immeasurable in terms of getting specifying the solutions and ensuring that those solutions are the right ones for the building over the life of the building. I know we kind of touted in the promotion of this webinar that we talk about what specific interventions then might come or might be suitable for sort of older and heritage buildings. I think really I can't stress enough how valuable it is to just prioritize the basics. As we've seen, lots of U values, airtightness, if it's coming out better than we'd previously assumed, 9 times out of 10, you can just make sure that walls aren't suffering from damp or defects, or just trying to really kind of go with the grain of the building, and can yield fantastic results in themselves. Just making sure the existing fabric is dry and performing as it was first built and intended, and actually you can then move on to frankly just prioritizing some really basic low-hanging fruit: loft insulation, draft stripping, air tightness, making sure you're complementing that air tightness with the right ventilation, and those combinations of things, and a great deal of have actually quite a well-performing building. And you can move on then to, I think about decarbonising the heating, thinking about a heat pump, thinking about solar panels and storage, without necessarily needing to go as deep as you might have otherwise previously thought on the fabric intervention side of things. Again, there's no silver bullet for these things. That's not going to be the case for all buildings. Obviously, there is, of course, going to be a strong case for upgrading fabric in certain instances, but yeah, I think just measuring, understanding what you're dealing with, making sure that the building is in good condition, defect free, the walls are dry, the timbers and the roof structure is dry and performing as intended, and take it from there, really. So real data unlocks safe, effective retrofit strategies. And as we've demonstrated in the talk today, we host a whole host of tools to enable more confident evidence-based decision making. So that concludes my talk. Well, just before we move on to Q&A, just want to flag that our next webinar will be looking at the subject matter of how do you combine these measurements to do better diagnosis of buildings and building issues. So combining multiple building performance measurements for maximum insight, and that one's running on the 27th of November. Thank you.
Brilliant, thank you for that, Luke. I hope people find that interesting. We've certainly got a nice number of questions to plough through, so we'll start at the top and we will see how far we get in 15 minutes. The first question is, will the slides be available and/or more detail or a link to the reports by EST and BTS on the 587 dwellings you mentioned near the start?
The slides absolutely will be made available, as you touched on earlier, Tanya. Will share a recording on our YouTube channel. The report we did with the Energy Saving Trust, that was originally commissioned by DESNZ. They've given us the green light to be presenting on it, and we've got a short summary paper that we can link you to. We'll include that in the follow-up to this webinar. DESNZ themselves haven't yet officially published the full study on their website. We've been nagging them for some time. It hasn't quite happened yet, but watch this space.
Yeah, absolutely. We'll make sure that's shared so you've got that extra bit of insight. The next question from Stuart. Can a measured U value be inputted into an RDSAP calc and still be compliant?
We are working closely with Elmhurst and Trustmark and the University of Salford actually on this matter, because it is a bit of a grey area. There is precedent. People have done it and been able to feed it through to a lodged EPC. We're trying to remove the greyness in the current wording of the conventions, and so I think the short answer is yes, you can do it. It's an open field. If it were to be called for audit, the immediate question would be, are you suitably confident and competent to be inputting a measured U value? And so you'd need to be a member of either an Elmhurst U value competent person scheme or a on construction energy assessor. But the way we see it, it's no different and no lesser risk than otherwise doing desktop based calculations on U values. But hopefully in the coming months we'll see further steps in this regard, and we'll see a more kind of concerted kind of clarification from BRE, Trustmark, and others in terms of the ability the explicit ability to do it.
Great, thank you. The next question is, through smart HTC systems and relative humidity measurements, you've mentioned it's possible to obtain a mold risk score. Would a short-term monitoring period around 3 weeks be sufficient for reliable results, or would you suggest calibration to reflect longer-term conditions?
It's true to say, obviously, mold risk is a dynamic affair. The conditions are going to vary over time. You would, as much as you can run the mold risk score with that smart HTC based 3 weeks worth of data and get a snapshot, an insight into the mold risk, it is absolutely true to say that you could run it for longer and observe sort of a more sort of variable trend. So I think the way we tend to think about it is mold risk is generally going to be higher in the winter, during the heating season. 3 weeks does tend to encapsulate quite a nice variety of kind of occupancy behaviours and variation in weather. But yeah, there's certainly no harm from a mold risk perspective in acknowledging that it is dynamic in measuring for longer periods of time. But yeah, all of that data can be readily uploaded to the mold risk indicator tool.
Okay, the next question is from Alex. How accurate is Heat 3D compared to a longer term heat plate type test?
Yeah, that's all on our website. We've done a lot of work, again, with the University of Salford and others in validating the Heat 3D method. And the way that we've done that validation is to do side-by-side heat flux plate monitoring and Heat 3D. And there is really close agreement. The level of uncertainty on the output is the comparable on both. Kind of both methods, you tend to cite kind of plus minus 15 to 20% uncertainty on those measurements. But yeah, in broad terms, all the reporting's there on our website, but both heat flux plates and Heat 3D measurements agree very closely across the testing that we've done.
Okay, the next question comes from Tom. Is there a best time of day or time of year to undertake a Heat 3D assessment?
Yeah, obviously both Heat 3D and Smart HTC, what we're measuring there is heat loss, and so they are limited to the winter heating season. We tend to be looking for in the order of kind of 7 to 10 degrees temperature difference between inside and out. Or alternatively, we just think of it in simple terms, kind of tends to October to March inclusive. Those 6 months tend to be your measurement season, and you want the property or the building in question to be positively heated at that circa kind of 20-degree set point, so that if it's 10 degrees or less outside, you've got that 10-degree difference that we're looking for.
Yeah. Next one is from Andrew. Have seen the differences in the U values. Have the differences in the U values seen been investigated for the impact of more moist walls, etc., or the quality of updates such as windows, doors, and other changes to the building over time?
Good question. It's not some. I'm sure some of the studies have gone into that. The slide I showed was a collection of different studies carried out by different bodies, and certainly the data that we have here at Build Test Solutions would be we've just got the measured U value and little else in terms of additional context. I'm sure that some of those other studies, however, will have looked into that to a greater or lesser degree, but I would support such a study or an investigation, because I think you would absolutely find that some of the higher U value numbers will be down to things like exposure level and sort of the moisture content and the sort of maybe presence of defects or trapped moisture in walls. And similarly, lower U values could be down to a well looked after building and good ventilation and so on. So that there is invariably going to be a relationship there with like the overall condition and state of repair of the building, and that what bearing that has on U value. But yeah, I'm not immediately aware of any particular study that's gone into great depth on that. But it's an interesting thought, actually. Yeah.
Okay, and rattling through them as fast as we can. Tommy has sent in, how would you prioritise improvements on heritage buildings? Would you look at air tightness first, then insulation, in situ U value assessments?
We do tend to try and couch our products as a bit of a triage approach. So I would start with a HTC measurement, understand the total rate of heat loss from the building. What are we dealing with in terms of its headline thermal performance? With that data, you then are also able to run the mold risk indicator. So are we dealing with really high internal humidity problems here? How well is the ventilation kind of managing the relative humidity? And so really high level insights into the building from HTC and mold risk, and have that actually inform what you do next. So if the building does have a high mold risk, understand if the ventilation is performing as intended. Is there any ventilation? You could then supplement that with an air tightness test to understand the relationship between air tightness and ventilation. If actually the HTC is returning as a low number, low heat loss, the mold risk score is low, then really you're confirming that perhaps the area of interest isn't necessarily wanting to be the fabric. You can move on to thinking about decarbonising the heating, or looking at PV and storage and things like that. So yeah, I think the HTC and the mold risk can help serve as a really useful headline indicator. We're certainly not naive to suggest you just dive into these buildings and do full-blown HTC mold risk U values, air tightness, ventilation flow rates every time. It's trying to take a pragmatic, sort of one step at a time sort of approach, and drill down as and when you think appropriate. But yeah, if a building had a really high HTC, hemorrhaging heat, you would then turn to U value measurements, air tightness, say what's the source of this heat loss exactly.
Great, thank you. Next one. Older buildings typically have thick solid walls, so high thermal value. How do you compensate for that when using the in situ U value measurement?
Yeah, so thermal mass is obviously both a really useful component of some of these older buildings that again, it's a massive consideration for, like, do you insulate internally and isolate that thermal mass or not? From a measurement perspective, it does present its challenges. With the U value side of things, in order for Heat 3D to work within that 1 hour window, the protocol is to preheat the space. So standard practice would be preheat to 10 degrees above external temperature for 24 hours prior to the measurement taking place. So the idea there is that you're saturating the thermal mass of that structure, then turning up to do the measurement, and included in the Heat 3D kit is a PID heating controller and a 500 watt heater. And part of the magic of the method is that you hold the internal temperature stable during that 1 hour time lapse. So again, a lot of work's gone into that and kind of how we manage the thermal mass side of things.
The next question from Will is one that we've had come up a lot recently, just generally. Can you measure U values of windows? Walls in traditional buildings seem to perform better than expected, but windows maybe not so.
It is possible to measure window center pane U values. Best done with a more conventional heat flux plate method, more so than Heat 3D, because it's thermography based. Unless you whitewash or kind of dull the reflectiveness of windows, Heat 3D won't work on those surfaces. So yeah, heat flux plates, you can do center pane U values. I would question the real value of that though, because I guess you could determine whether a double glazed unit has failed or has had trapped air. For a single pane of glass, I think we can all quite quickly conclude that the U value is going to be fairly woeful. What's really hard to acknowledge, that you're right, the windows can often be a weak point, but it's more the thermal bridging and like the interface of the glass to the frame and the surface area that the frame represents. And quite often, if we're dealing timber slash frame, single glazed window, quite often actually the performance deficit is more in the window seals and the air tightness, the draftiness of them. So yeah, there are limitations to how far you can go with measuring specifically an individual window unit. But again, HTC would pick that up. So you're measuring the whole building heat loss rate. So you could the other way of approaching it actually would be to work backwards, measure the HTC, then maybe measure some U values, and almost what's left is the thermal. If you measured air tightness as well, what would be left is the thermal bridging and the window heat loss. But it's a judgment you could make depending on the building and the nature of sort of how much of the overall heat loss surface area do the windows represent exactly.
Great, thank you. I'm going to squeeze one more in. I'm aware of the time is ticking on. Those questions that we haven't got to, we will reach out to you individually and follow up. So the last one for today, do the tools work the same way depending on weather conditions? Are any of them season specific?
Yeah, so Smart HTC Heat 3D, as we've touched on, it's a winter season measurement, October to March inclusive. There does need to be positive heat transfer from inside to out. Mold risk you can do year round, but invariably you're going to see lower mold risk scores in the summer than winter when you've got higher external, internal humidity levels. Air tightness testing, ventilation flow rate testing, you can absolutely do year round, no problem at all.
Thank you for watching our webinar today. We hope you found it useful. If you have any other questions you would like to chat to the team about, please do not hesitate to get in touch via the details on the screen, and we'll see you at the next one.